The task of a standard power supply is rectification, stepping down, and stabilizing voltage. Accordingly, such devices always contain a rectifier, a step-down transformer, and a stabilization circuit. The implementation of all these units, however, can vary greatly depending on the purpose of the power supply. So before we build one, we must decide on its parameters. I suggest starting with a regular USB charger. One can find use for such a device in every home. The unit that we usually call a USB wall charger is in fact not a charger, but a stabilized power supply of 5 volts DC. So the first part that we're going to need is the step-down transformer. Here's what I found in my inventory. Which one is right for us? In a classic power supply, 220 volts or 110 volts, depending on your country, is supplied directly to the primary winding. So, if we do not make sure that the part is rated for this particular voltage and frequency of 50 or again 60 Hz, the experiment can end in failure both for the poor fellow transformer and wiring in your house. The easiest way to determine the suitability of a component is check its part number. Out of all candidates, only one has it pretty much informative. This text should be understood like this. The primary coil, red are the 2 red wires, is designed for 220 volts and frequency of 50 Hz. The secondary coil, yellow 2 yellow wires, outputs 8 volts AC with a current of 0.8 amperes. The 0.8 is the top output current this transformer can produce, which yields output power of about 6.4 watts. So what happens if we apply a greater load to it? Well, it should be understood that the transformer is, in fact, a pump for transferring energy, and each particular model can push exactly as much as intended by the manufacturer. So if we increase the load and force this transformer to produce current above 0.8 amperes, the output voltage will likely start to drop. In this case, the part will heat up and may even fail. So when building a power supply, the very first thing you should consider is the power rating of your transformer. Let us measure the resistance of the coils. As we already know which is which, everything is simple here. The primary winding resistance is around 300 ohms. The secondary, a little less than an ohm. As we know, transformers are used to convert, that is, step-up or step-down voltage. So the main parameter of the device is the transformation ratio, which is defined as the ratio of the input voltage to the output voltage. For example, if you feed 50 volts to a transformer and get 10 volts at the output, its transformation ratio is 5. If 3 volts is applied to the input and 30 is obtained at the output, yes, it's also possible, the ratio is 1/10. So all step-down transformers have their ratio greater than 1, while the step-up transformers have it below 1. However, in theory, any transformer can be turned from a step-down into a step-up simply by swapping the primary and secondary windings, and vice versa. The transformation ratio directly depends on the number of turns of the windings. And if you wind a transformer, for example, with a primary of 1000 turns and a secondary of 100 turns, you will get a device with a ratio of 10. If the number of turns is all that counts, it looks like we can figure out the transformation ratio by coil resistance, which is directly proportional to wire length. Let's check it in this transformer. If it inputs 220 volts and outputs 8 volts, its transformation ratio should be 27.5. However, the winding resistance ratio, as we can see, is more than 300. How to explain it? The answer is actually quite simple. You can pause the video and take a second to think. The thing is that primary and secondary coils use wire of different gauge, which means that its resistance per unit of length is also different. I think it's quite remarkable that gauge and resistance have absolutely no effect on transformation ratio. The number of turns is all that counts. But, mind you, provided that the width of the primary and secondary coils is the same. Why do transformers use winding wire of different gauge? The reason is that gauge determines current that is allowed to flow through the winding. The larger the gauge, the greater the current. If we imagine that the transformer is an ideal device, then the amount of energy flowing in and flowing out of it should be the same. And since the work done by electric current is equal to the product of voltage, current, and time, the essence of the processes occurring in it is described by the formula that you can see on the screen. So, as the voltage is stepped down, the current will increase. And as the voltage is stepped up, the current will decrease. That is why in step-down transformers, the secondary winding always uses a wire of a larger gauge than the primary. If it's a step-up transformer, the current of the secondary coil, on the contrary, will be lower, so it will use the wire of smaller diameter. You can try and substitute different values into this formula and see how it works. What conclusion can we draw from that? Looks like resistance will not aid us in figuring out the transformation ratio, but it will definitely make it clear where the primary is and where the secondary is, because the difference in wire gauge only increases difference in resistance. So, if we consider a stepping-down transformer, the winding with the greatest resistance will always be the primary. Let's check the remaining transformers with multimeter and see. Here we have no circuit, which means that this transformer has probably failed. It's a shame. It's the largest, which supposedly makes it the most powerful. Let's put it aside and proceed. What do we got here? 3 ohms? Half a kilo. I think it's obvious which one is the primary. Let's put some marks here. And yet another transformer. 900 ohms, 1.4 ohms. Marking. And the last one. As we can see, this one has many leads both at the primary and secondary side. It's highly likely it was installed in a switched power supply. We'll talk about them later, which means it's not suitable for our purposes. Okay. Is it possible to feed 220 volts to these transformers? Let us reason. All these devices have pretty much the same dimensions, which means their power is also approximately the same. The primary coil resistance is also roughly the same. As you remember, it's 300, 500, and 900 ohms. Also, the transformer that has the lowest primary coil resistance is intended to be used in 220 volt circuits for sure. We can gather that from the designations on its body. So, common sense suggests that all these transformers, in this case, must be rated for 220 volts. We can't be 100% sure, of course, but none of them has the primary coil resistance of 20 ohms, for example. If they had, with the same dimensions, this would definitely be a reason to stop and think. I believe you got the idea. At the same time, there is no specific correct resistance for the primary winding of a 220 volts transformer. This is also important to understand. After all, the resistance, as we said, depends on the wire gauge. And in general, the higher the power rating of the transformer, the lower the resistance of the windings. For example, the resistance of the primary winding of the power transformer in an old-school CRT TV was about 8 ohms. And here another reasonable question arises. How is it that such a transformer does not create a short circuit in the wall outlet. If we apply Ohm's law here and calculate current, the formula yields the huge value of 30 amps, or 6.6 kilowatts. No TV can consume that much. The reason is that the transformer is an inductor, and its resistance, when exposed to alternating current, increases. It's even got another name: reactance. Note that inductive resistance is denoted X in physics, not R. This is explained by the fact that this is a different physical quantity. After all, the coil still has the regular resistance, which can be measured by a multimeter, and it's still 8 ohms. Inductive resistance, X, is effective only when the coil is exposed to alternating current. It's important to understand that reactance also depends on the frequency of the AC. So if you have a transformer designed for a frequency of 500 Hz, you cannot connect it to wall outlet, even if it's rated for 220 volts. But as they say, practice is the best master. Because we are not 100% sure that the two remaining transformers are fit to work with 220 volts, we must make some precautions. You've probably noticed that in all my videos dealing with high voltage, I use a double circuit breaker. We will also use it today. Let's start with a simple test. We'll measure the current flowing through the primary winding without load. It's also called the idle current. This will help us understand whether the transformer is rated for 220 volts. If the current is too high, it obviously means that it's not. When performing such a measurement, there is one important nuance. At startup, a large pulse current will flow briefly through the coil, similar to how it happens in electric motors. It's called inrush current. In order not to kill the multimeter, we must temporarily short its probes as we power on our circuit. Okay, let's do it. Removing the jump wire from the multimeter probes. The idle current here is 15 milliamps, which yields power leakage of about 3 watts. A bit too much, but not fatal. Next one. Also about 15 milliamps. This suggests that the transformers have similar parameters. And here, idle current is 40 milliamps, while the transformer is explicitly rated for 220 volts. That's odd. Probably means it's got some problems with its core. That's 9 watts leakage. This transformer will heat up even in idle mode, but it doesn't matter much for our experiment anyway. Now let's measure output voltage. Let me remind you, we are building a USB wall adapter. Because we are going to use a step-down voltage regulator, which assumes voltage drop, transformer's output voltage must be greater than the target value, that is, greater than 5 volts. It shouldn't, however, be too high, otherwise the regulator will heat up. Okay, here we got 8.8 volts, just like it says. Here we have 8.5. And here we got 17 volts. This transformer will clearly not work for us. If we use it, the voltage drop on the regulator will be as much as 12 volts, which will yield 6 watts of power leakage at current of 500 milliamps. 6 watts is too much. So let's put this one aside. Okay, the voltage that we have just measured is alternating. We need to rectify it. As you probably know, for that purpose, they use bridge rectifier. This component is basically an integrated circuit consisting of 4 diodes wired in a bridge. If you don't have the bridge IC on hand, you can build one. I found this circuit in my inventory. It contains a bridge based on 1N4002 diodes. Will it work? To find out, let us first brush up on how the bridge rectifier works. It's quite simple actually. Alternating current consisting of 2 half waves is fed to the input. If we consider half waves as two states of the rectifier, then the current in the first state will flow like this, and in the second state like this. As a result, we get direct current at the output because no matter the input polarity, the positive pole will always end up here, and the negative pole here. What are the requirements for the bridge diodes? Well, first of all, they must be rated for the desired voltage. Note that we mean here the reverse voltage, the one that is present at the terminals of the diode when it is switched off, that is, in these cases. If the limit value is exceeded, the diode will fail. In our case, the reverse voltage is very low, which means we do not need to worry about this parameter. As for the power limit, in a diode bridge, it is calculated based on the current which will flow through the load, and it should be slightly greater than that. For example, if you want to power a 1 kW motor with a supply voltage of 220 volts, the current will be approximately 4.5 amperes. In this case, you can use diodes rated for a current of 5 amps. Note that the diodes, however, are not required to have a power of 1 kW, since their voltage drop is very small, only about 1 volt under load. Since 2 diodes are on at a time, the total power dissipated at a current of 4.5 amperes will be about 9 watts. The 1N4002 has a reverse voltage of 100 volts and a current rating of 1 ampere, so it will work for us. Let's check out our bridge. Diodes usually have their cathode marked with a white stripe. The output of the bridge are the nodes where diodes are connected with same poles. This board already has designations, but let's imagine we need to figure out the bridge pinout. Let's use a marker to draw wires on the top side of the board. We can see 2 anodes connect here. This will be the negative output. 2 cathodes are connected here. This is the positive output. The 2 remaining nodes are, obviously, the AC input. Let us solder the board to our transformer. Polarity doesn't matter. Okay, so we got 7.4 volts at the output of the bridge. This isn't exactly direct current, it's pulsating direct current, or PDC. It's called that because the oscillations of the input AC are copied at the output of the bridge, only the polarity doesn't alternate. To smooth out the ripple, a capacitor is traditionally installed at the output of the diode bridge. Our board has a placeholder for it. When choosing the capacitor voltage rating, we have to bear in mind that after smoothing, the voltage at the output of the bridge rectifier will increase. When measuring alternating voltage, the multimeter does not display the real signal amplitude, that is, the amplitude of the sinusoid, but the average, or the so-called effective value, or root mean square, RMS, which is a root of 2 times less than the real one. When we attach a capacitor to the output of the bridge, it charges up to voltage peak values, which explains why the voltage appears increased. This means we cannot use a 10 volts rated capacitor here. I will use a 16 volts 1500 microfarad capacitor instead. Okay, here's what we got so far, and the output voltage of our power supply is about 11.5 volts DC. The next thing we need here is the voltage regulator. Why? Well, it seems obvious. So that the output voltage does not depend on the voltage in the wall outlet. It is true, but it's sort of not exactly that. Let us try to attach some load to the output of our power supply and see what happens. Looks like we got a significant voltage drop. If we connect here a real load, like something CPU-based, it will be even worse. The output voltage will fluctuate, and the device will constantly reboot. To stabilize output voltage, we need to use here the part called Zener diode. It's a semiconductor that reacts to an increase in voltage by a sharp decrease in resistance. How does it work? Every Zener diode has a rating, expressed in volts, called breakdown voltage. This particular part, for example, is rated at 6.2 volts. While the voltage at Zener diode's leads is below its rating, it's off and current is not flowing. As soon as the voltage hits the breakdown value, the Zener diode switches on and the current rises sharply. This way, the component resists a further increase in voltage. A Zener diode can be compared to a piston which has a tight spring installed on its bottom. Until the spring touches the stop, the rod moves freely inside the cylinder. At the end of the range, the spring begins to resist and a significant effort is required to further move the rod. In the same way, a Zener diode reacts to a voltage rise above its breakdown value. A Zener diode can be easily confused with a diode. In fact, it is a diode, but with one significant difference. When current flows through the diode in the opposite direction, nothing happens, but for the Zener diode, the reverse polarity is the working one. This means, and this must be remembered, that its cathode is connected to the positive pole and the anode to the negative pole. This is called reverse biasing or breakdown. That's what makes the Zener diode perform its stabilizing function. Let's wire the Zener diode to our power supply and observe its operation. Like I said, for the part to switch on, the voltage on its leads must be greater than the breakdown rating, which means we must wire it in parallel to the output of the supply. However, there's another significant nuance here. Because the breakdown resistance of the Zener diode is very low, a significant current may flow through it, which could cause the device to quickly fail. That means the voltage may be fed to the Zener diode only with a current-limiting resistor in series. The value of the resistor is chosen so that the current is sufficient to make the Zener diode switch on. I used a 6.7K resistor. As we can see, the voltage on our diode is now set at 6.1 volts. Theoretically, this power supply can already be used. Its output is stabilized, because change of voltage in the wall outlet will not affect the output voltage. If you are making a power supply for a low current load, such as an operational amplifier for example, it's quite possible that it will suffice. But in the case of a USB charger, this circuit cannot be used, because due to the large drop across the resistor, it won't provide enough current. To increase output current, we are supposed to reduce the value of the resistor. But in this case, a large current will flow through the entire circuit, including the Zener diode, which will cause it to overheat and fail. What are we supposed to do then? Here, a common collector amplifier, also known as an emitter follower, will come to the rescue. This topology, based on a single transistor, copies the voltage fed to its input and provides current amplification, which is exactly what we need. In this circuit, the collector is connected to the common power rail. The emitter drives the load, and the base terminal of the transistor serves as the input. The R1 resistor provides the D2 Zener diode with current, so node A will have the potential equal to its rating. The emitter follower will copy this voltage and feed it to the load. At the same time, the load current will not flow through the Zener diode, but through the transistor. And this is a classic configuration found in textbooks. But you have probably seen it shown like this. If you look closely, it's easy to see that it's the same schematic. The Zener diode is connected in series with the resistor to the positive power rail. The anode potential is fed to the transistor's base, the load is connected to the emitter, and the collector is wired to the positive power rail. Please note, this is just a classic emitter follower. It is not the common base configuration. They do look similar, but essentially have nothing in common. When analyzing any schematic diagram, always focus on the actual connection of the elements and not on the visual similarity. Let's finally put together our stabilizer. I found a transistor. Again in my inventory, it's a BD437. It looks a bit worn, but who cares? According to the datasheet, this is an NPN transistor, rated for a current of 4 amps and a voltage of 45 volts. Exactly what we need. Let's check it. Looks like it's not dead. Don't forget to also check the emitter collector circuit. With both junctions intact, it still can be shorted. But this one is alright. We are going to put a 100K resistor parallel to the output of the stabilizer. It's needed to provide current to the emitter when load is absent. Before connecting load, we want to know what voltage we got at the output. We also have to keep in mind that there is a drop of around 0.6 volts at the base emitter junction. This means that the output voltage will be a bit lower than the value of the Zener diode. Given the above, I installed a Zener diode with a nominal value of 5.9 volts into the circuit. Okay, everything's ready and we can power on. Let us first check voltage at the base of the BD437. It's 5.9 volts. And now at the emitter, as planned, 5.5 volts. Great! Let us solder the USB-A socket and an output capacitor. A capacitor is installed parallel to the output for stability and better transient response. It also smooths out spikes and dips in voltage and prevents self-excitation of the circuit. Okay, let's check it. I'm connecting the USB tester to the output of our circuit. Everything's working as intended. Let's try to connect load. And we can see the voltage drop. Why is it happening? Maybe the transformer cannot manage the load. Checking voltage at the bridge output? Nope, we got 9 volts here. So it looks like it's the transistor that's responsible for the voltage drop. But why? What do we got at its base? It's 5 volts instead of 5.9. That means the voltage drop occurred at node A, the Zener diode. But why? You can pause the video and take a moment to think if you wish. The reason is that, after connecting the load, the emitter current was increased, which also led to an increase in the base current. As we know, these two values are linked by the current gain of the transistor. That's how it works. So the currents that flowed through the Zener diode and the base emitter junction added up. So the resistor R1 failed to provide enough current to power the Zener. Let's reduce its resistance from 6.7K to 2K. Checking out. Now our circuit is working as intended. So the final schematic diagram of our power supply will look like this. I added a switch and a fuse in series with the primary coil. Let's go over it again, just to be sure. The AC from the secondary winding of the transformer is fed to the bridge rectifier. At the output of the rectifier, after attaching the smoothing capacitor, we get 11.5 volts. This voltage is fed to the R1 D2 circuit and is divided between these two components. The voltage at D2 sets equal to its rating, that is 5.9 volts. The voltage at the resistor is the difference of voltages, 11.5 minus 5.9 is 5.6 volts approximately. 5.9 volts from the anode is fed to the base of the transistor, which is installed in common collector configuration and works as an emitter follower. The anode voltage minus the drop across the emitter base junction is replicated at the emitter of the transistor. The voltage regulator that we have just built is called Parametric. It's got its name thanks to the fact that the voltage at its output is maintained due to the parameters of the parts used in it. Let us now try to evaluate the performance and efficiency of our stabilizer. It's very easy to do. We will wire an ammeter in series with the primary coil. By multiplying its readings by 220 volts, we will get the power consumption. The output power will be measured using the USB tester. Okay, so the consumption at the wall outlet is around 11 watts. The output power is around 2 watts. The efficiency isn't that great really, but it's explained by the losses within the transformer. As you remember, its idle current was 40 mA, which yields energy loss of around 9 watts. If you don't want to bother building your own voltage regulator, you can use an IC. I mean the popular LM7805. Let us try to replace our regulator circuit with the 7805 and check how it works. As we can see, the output voltage is present. Attaching load, the voltage drop at the output is a bit larger. How about efficiency? The power consumption at wall outlet is also higher, probably because of a lower input voltage. Regulators in which voltage difference between the power source and the load drops on the stabilizing element are called linear. Linear regulators, unfortunately, are not very efficient in terms of energy, but they are simple in circuitry and can provide very accurate stabilization. For example, they are used in measuring and sound equipment, where noise immunity is top priority. In all other cases, switching power supplies are used. The principles of operation and circuitry over switching power supply are quite different from a classic low-frequency unit. The main difference is that in the switch supply, the voltage is first rectified and then stepped down. Since DC voltage cannot be fed to the transformer, the switching supply has a high-frequency generator. The use of high frequencies makes it possible to significantly reduce the dimensions of transformer without reducing its power. Stabilization in such devices is implemented using a feedback loop, which continuously pulls the voltage at the output and varies the amount of energy supplied to the transformer. Operation of such circuits has been covered in my videos about the ATX power supply and the blocking oscillator. The links you may find in the description. And finally, we can get closer to efficiency of switched power supplies if we use a DC-DC step-down buck converter. How do we do it? It's quite simple actually. We just wire the device to the output of the bridge rectifier. Let us set the DC output to 5 volts and attach our smartphone to the output. As we can see, the DC-DC board handles load much better. The voltage drop at the output is negligible. And what about efficiency? The current at the input is only 40 mA, which is a much better result than both previous circuits that we have built. Okay, let's sum it up. Using the method shown in this video, you can assemble a power supply of almost any power and for any voltage without much effort, provided that you use a transformer, a bridge rectifier, and a regulator with the desired parameters. However, if you do not want to bother and are looking for a particular power supply or a powerful DC-DC converter board, you can order them online using the links found in the description. That would be it for today. Please don't forget to comment, share and subscribe. If you liked the video, please support me by dropping some Bitcoin or Ether to the wallet addresses listed in the description of this video. This was Ron Martino. See you next week.